Hello students, next let us look at the last theorem of module 2, which is the maximum power transfer theorem. In case of maximum power transfer theorem, the theorem is different for DC and AC. So we will deal with each of them separately. First here, right now we will discuss with the DC maximum power transfer theorem. It's very easy. Once you understand the theorem, you have to use basically Thevenin's for solving the problem. So it's not at all a difficult problem, but the maximum power transfer theorem is the only theorem for which you have to study the proof. For the other theorems, generally the proof is not asked. Okay, so let's go for the maximum power transfer theorem DC. What is the statement? The statement says that if you are having any source, okay, so here there is a voltage source with some internal resistance, source resistance Rs. What the maximum power transfer theorem says is that the maximum power is delivered, that means the maximum power from the source. That maximum power is delivered to the load. So the maximum power is delivered from source to a load when the load resistance, so this is the load, when the load resistance is equal to the source resistance. That means when RL is going to be equal to RS, at that time we will have the maximum power being delivered from here to the load, from the source to the load. Now, generally maximum power transfer theorem, you will use it in many different places. Just to give you a simple example, okay, you all might be interested to listen to music, isn't it? So if I am suppose having a mobile phone, in which a smartphone, in which from which I am trying to listen music, then I will connect my music to, I will connect the jack output to a set of earphones. Okay, so let me draw it. So I will connect it to a set of earphones for my left and right ears. Okay, and this is what I am basically using for listening to music. Now if I am going to concentrate on just as this being the source, okay, and this being the load. What is the load? The earphone is the load. Okay, the earphone is the load. So what maximum power transfer theorem says is that if you want to get your signal very nicely or very, with full power, maximum power, if you want to take the maximum power from here and deliver it all the way to your load resistance, which is your earphone, then the earphone resistance should be equal to the source resistance. Okay, it should be equal to the source resistance. Otherwise, what will happen is the power will basically reflect back. I am not going deeply into that, but this is just one of the applications. Even in your cable TV, if you are having a cable set-top box, from there if it is connected to a TV, then this is the source and this is the load. And at these two connection points, we have to make sure that the source resistance and the load resistance are all same. Otherwise, the signal will not go from here to the television and you won't be able to see anything. Like that, wherever you want to send some signal, whether it is in telephones, whether it is in internet, whether it is in this cable TV, wherever you want to send a signal from some source to some load, you have to always take care of this particular scenario wherein the source resistance should be equal to the load resistance. So this is going to come again, when you will study in electromagnetic theory, when you will study application based subjects, everywhere this thing will time and again come by. Even in your electronic circuits, or when you are going to study about operation amplifiers, op amps, everywhere this thing will again and again come. So this is something that you should, take really very seriously, and try to remember this, that the load resistance should be equal to the source resistance for maximum power to deliver from the source. So now let us prove it. For proving it, what we are going to do is we are going to assume that there is a source resistance Rs and there is a load resistance RL and there is a energy giving or power giving source V. So this Rs can be the resistance of V, the internal resistance of V, or as I have drawn this whole box may represent a network. It may represent a network, and the whole network is represented by a voltage and a resistance. Do you remember what that is? That is the Thevenin's theorem, isn't it? So you are having a source voltage and a source resistance representing the whole network. So in this subject, it will be basically a network which you have to convert it into this Thevenin's format so that you are getting it correctly. So let us prove it. Okay, so what is the power delivered to the load? Okay, for that first I have to find out the current I, the current I, which is I, this is the I. So there is only one voltage and there is a current. So I can straight away write it will be going to be voltage divided by the total resistance, which is the source resistance plus the load resistance. Okay. Then power delivered to the load. The power delivered to the load is basically, I can write the power as, so the load is RL, so the power which is delivered to the load, I can write it as power, you all know, is V into I, or even I square R. Here what is the R? It is the load resistance RL. Therefore I will use this formula. So power is going to be equal to I square RL. I square I have already written here, so I can write this as V square divided by Rs plus RL the whole square, okay, into RL. Clear? Or I can take RL inside, that is also not a problem. I can take RL inside and add directly, no need to keep any brackets. So this is the power. So let me write this as equation number 1. Now for power to be maximum, what is the condition? For power to be maximum, what is the condition? See what I am trying to say here. Here we are having a source resistance which is not going to change. The voltage is also not going to change. The only thing that can change here is RL. So the power may vary with respect to RL as it is written here. So the power will vary with respect to RL, isn't it? In this equation it is written that you are having RL here and you are having RL in the denominator. Of course they don't cancel off. So you can say that the power basically varies with respect to RL only, if the voltage and the source resistance are not changing, which generally do not change. So if we want to find out what is the maximum power for changing RL, then you all know mathematically what is the equation. So if you want to find out what is the maximum quantity of power that can be achieved for varying power, or if you want to find out what is the power, the changing power, with respect to RL, then basically the formula is, for maximum it is dP by dRL should be equal to 0. That means whenever the change in power is going to be equal to 0, at that time, at that particular value of RL, we will have the maximum power. So it's something like this. See, if you are going to change the value of RL, and the power is going to change, then so when RL is equal to 0, the power may be 0. Slowly when the RL goes up, slowly when the RL climbs up, see, it will go up, correct? But see, when RL is going to be very high value, in the denominator you are having RL square. So as you go forward, after a certain time, this value, this RL value that is in the denominator, which is square, that particular value in the denominator will keep on increasing, whereas the numerator will not that much increase. So what will happen after some time, this will come down. Okay, so it will have this kind of a curve, and wherever the maximum power occurs, we want to find out that value of RL wherein the P max occurs. Okay, so if this is the curve and it is rate of change of dP with respect to RL, then we all know that this point will occur whenever dP by dRL is equal to 0. This is the maximum condition that you have studied in maxima minima condition. So dP with respect to RL. For doing that, basically we have to do the differentiation. So dP by dRL of P. Okay, so we all know what is the formula. It is denominator. So let me write the equation so that you all get familiar to it. So it is going to be V square. Only RL is the term, so V square is going to be constant, so that I will take outside. Now I have to take RL divided by RS plus RL square. Both numerator and denominator has. So first I will write the denominator, which is RS plus RL square into differentiation of RL with respect to RL, which comes out to be 1 minus, then we are having the numerator RL, okay, multiplied with the differentiation with respect to RL of the denominator, which is RS plus RL the whole square, that divided by the denominator square. So it is RS plus RL square, the whole square will give me 4. Okay, that will give me 4. So let me do this. So let me come down. Okay, so it is going to be d by dRL of power is going to be V square is as such going to be there. Now let us see what happens in the numerator. In the numerator, this one becomes 1. So it is going to be RS. It is going to be RS plus RL the whole square into 1 minus RL, then this differentiation 2 will come outside, so it is going to be 2 times, then RS plus RL, if you want to differentiate, the answer will be 1. So it is going to be RS plus RL divided by RS plus RL the whole raised to power 4. Okay, and this should be equal to, according to minimum maxima condition, this should be equal to 0. So if this has to be 0, then this is constant, so this can't be 0, V square can't be 0. Okay, V square can't be 0. And then what about the denominator? The denominator we can't make infinity, because with infinity we cannot write. So what is the only term that can be made 0 here is this numerator. So what I will do is, I will straight away, this equation reduces to, therefore for this condition to satisfy, I should write the numerator RS plus RL square minus 2 RL, then RS plus RL is equal to 0. From which if I take RS plus RL common, then I will write RS plus RL. I am taking one of them as common. So this becomes 1 minus Okay, 1 minus 2 RL. Okay, or instead of taking this thing, what I will do is I will expand it. Let me expand it. That is much better. Okay, so this will become RS square plus RL square plus 2RS RL minus, here it is going to be 2RL RS, 2RL RS minus 2RL square is equal to 0, from which these two will cancel off and these two will also cancel off, not cancel off exactly. I will basically get RS square minus RL square is equal to 0. Okay, so I will not cancel it. Let me not cancel it. Okay, so it will basically, I will get minus RL out of it, from which I can basically say, no, it's very simple now, from which I can very clearly say that RS square should be equal to RL square, or RS should be equal to RL. And this is the simple proof. This is the simple proof that the source resistance should be equal to the load resistance for maximum power transfer. Okay, so the last statement that I will write it, let me write it using a different color. So for maximum power transfer, to take place, RS should be equal to RL, or the source resistance should be equal to load resistance. So this is the proof. And based on this, what are the steps for doing? Okay, steps for solving power transfer, maximum power transfer. So I will write like this: steps to solve maximum power transfer theorem numericals. The steps to follow for the case of maximum power transfer theorem. Okay, so let me write the steps one by one. So the first step will be that whatever be the circuit, we have to remove the variable load. Okay, that means let me draw here with an example, otherwise you all may get, suppose there is some source here and there is some resistance value here, something here, resistance here, and finally there is some resistance in which I want to find out the load. So let me draw it in a different color. Okay, so what it says is, first you have to remove the variable load. So this is the variable load in which I want the maximum power to transfer. Okay, so the first thing that we do is we remove this particular variable load. So we remove this particular variable load. Okay, and then so variable load RL. Okay, then the second step is solve and find VTH and RTH from terminal AB. So now where is terminal AB? Here, after removing the load resistance, whatever remains, we will have terminal AB. And now what we have to do is we have to find out VTH. So this is going to be plus minus VTH. We have to find that. Similarly, we have to find out what is going to be the RTH. Okay. Then what is the case? Then we find out the third step is make RL equal to RTH. So how does the diagram looks like? See, we are basically converting. Let me draw the network. Okay, so suppose if this is the network, and that network we have converted into now. That network now we have converted into a Thevenin's equivalent with RTH and VTH. Okay, that network we have converted, and let me write the values also. So let me write it in black. Okay, so this is going to be your VTH and this is going to be a RTH, and then we connect the load resistance. The load resistance is RL. Okay, the condition says that your RL should be equal to RTH, whatever is the resistance that you have found out here, the Thevenin's resistance, that you have to put here. So that makes it the condition for maximum power transfer. So now once you have made this, the last step is to find the power. Okay, the fourth is that we find out power. So the maximum power is calculated as so now let me remove this circuit. Okay, let it remain there. Okay, so how do we calculate it? We all know that the power that we calculate is generally given by P power is equal to the current, the maximum current. So not maximum current, the current. Okay, now suppose the current I am going to draw here as some load current IL. Okay, so the power is going to be IL square into RL, where RL is actually your RTH. So I will write this as RL. So this is going to be IL square RTH. Okay, for maximum power, this will become P max. Okay, this is the maximum power. So when I want the maximum power, RL should be equal to RTH, that we have written. What is IL? IL is going to be V square divided by RTH plus RL the whole square. Now where did I get this one from? What is IL here? IL is here going to be equal to VTH divided by RTH plus RL. Okay, but RL is RTH, so IL square is going to be the square of this, and that is what I have written here. Okay, VTH square into RTH, but I already know that RL is what? RL is RTH, so this becomes VTH square RTH divided by RTH plus RL. RL is also RTH, so this becomes 2 RTH the whole square. Okay, from which I will get VTH square, and the RTH at the numerator will be cancelled by 1 of the RTH at the denominator, but 2 square I will already have, so it is going to be 4 RTH. Therefore, I can very clearly say, and that I am going to put it in a box. Okay, that I am going to put it in a box, and that formula is P max in such a case is going to be whatever is VTH square divided by 4 times RTH. So this is for DC. Remember, this is for DC, because for AC the equation will change. That again we will have to derive. So this is the step that we have to do for solving the maximum power transfer theorem. Okay, thank you.